Alright, so in this video I'm going to be explaining another important article with the title Toward Sparsification of Graph Neural Networks. So this paper in 2023. As real-world graphs expand in size, larger GNN models with billions of parameters are deployed. High parameter count in such models makes training and inference and graph expensive and challenging. To reduce the computational memory costs of GNNs, optimization methods such as pruning the redundant nodes and edges in the input graphs have been commonly adopted. However, model compression, which directly targets the sparsification of model layers, has been mostly limited to traditional deep neural networks used for tasks such as image classification and object detection. So we utilize two state-of-the-art model compression methods, train and prune, sparse training for sparsification of weight layers in GNNs. We evaluate, compare the efficiency of both methods in terms of accuracy, training sparsity, and training flops on real-world graphs. Our experiment results show that Wikitalk, Stack Overflow datasets for link prediction, sparse training with much lower training flops achieves a comparable accuracy with the train and prune method. So this is a graph convolution network structure. There are currently two main approaches for reducing GNN training and inference complexity by sparsification, simplifying the input graph and sparsifying the model. The first approach, which utilizes pruning or sampling of the nodes or edges in input graph, has been extensively used. On the other hand, while model compression is well studied for traditional deep neural networks, it is an underexplored area in the context of GNNs. The second model, sparsification, is a sparse training, which starts the sparsification process of neural network layers directly from the beginning of training, using even fewer training iterations compared to dense training. Sparse training fixes the model sparsity at the beginning of the training and uses drop and grow policy to explore the sparse model architecture that yields the highest accuracy. It is the core of sparse training, as a large number of weights are switched between 0 and non-zero. Such frequent memory write and read operations heavily impact system performance. A proper drop and grow policy could significantly improve the temporal and spatial locality. Moreover, having a fixed sparsity throughout the training allows sparse training to reduce the computation and memory footprint of both training and inference stages. So we apply and compare train and prune and sparse training methods in the context of graph learning. So graph learning representation learning, we call it GRL. Such GRL techniques is based on performing random walks on a graph. Random walks capture the node properties by randomly visiting adjacent nodes. Random walks are then fed to word-to-vec skipgram, just like a natural language processing that I've explained skipgram. We can use this paradigm. So they capture node properties by randomly visiting adjacent nodes. And random walks are then fed to word-to-vec skipgram model, which is a natural language processing technique to capture node embedding. For example, we have one word and surrounding. Same for because a random walk is a sequence of nodes, so we get the middle one and the surrounding, you get the surrounding. So these node embeddings are fed into downstream graph learning tasks such as link prediction or node classification. Graph learning is a well-studied problem, and there are many different techniques for it. GNS, GCN, Graph Sage, and Graph Attention Network are some of the techniques for learning inductive node embeddings that combine external node features into neural network models. So here we have these sparsifiers. You see this sparsification of a two-layer fit FNN. Given a graph, the GRL algorithm computes the embeddings of node U and feeds it to the input layer of the feed-forward neural network. It then propagates the node embedding through its layers to output a prediction L sub U. So we specifically focus on weight matrices sparsification. So we jump to that. What is weight pruning using SLR? So consider a graph GNN with n layers where the weights at layer n are denoted by W. I have an article. I used ADMM for a bipartite graph in the context of natural language processing. So it's very important. This ADMM is very efficient. In the ADMM and SLR training, the loss function can be defined like this. The thing that I don't like about this, we are writing a function of the weight. Our brain doesn't do such thing. Doesn't care about the weight of the edges, and is not optimizing explicitly like this. It does some process, some simulation. So we need to think about why we don't follow the biologically inspired neural networks. So let's carry on. In the ADMM, the loss can be defined like this for each layer. The first term represents a nonlinear smooth function, and the second term represents non-differentiable cardinality penalty term, which ensures the number of non-zero weights are less than or equal to the predefined number within each layer. The objective is to minimize the loss function. However, because the loss function is subject to constraints on the cardinality of weights, it cannot be solved in its entirety. So SLR techniques decompose the problem into two smaller subproblems by introducing duplicate variables. So here, WN, but it's a duplicate variable, Wn, Zn. That's it. You got the idea. That is the augmented Lagrangian function here. Augmented Lagrangian function. But we also add this trace and this Frobenius norm to make sure they are the same, because we are saying explicitly they are duplicates. So we need to prove it in our optimization. So that's why we put it explicitly in our objective. And after the decomposition, the subproblems are solved iteratively in two steps. First, solves the loss function problem for Wn by using stochastic gradient descent. So once you solved it, then solve cardinality subproblem Z sub n through pruning by using projection into discrete subspace. So the subproblem can be solved by stochastic gradient descent. However, an additional surrogate optimality condition for updating the multipliers is used as follows. So if this condition is satisfied, multipliers are updated using this. And the step size is now this S sub k. The step size can be defined as alpha k, and the second sub-problem is solved with respect to z sub n, while fixing other variables at values w. For example, it reminds me by level optimization. Sometimes it's like coordinate gradient descent. You have two blocks that here are identical. That's why we are minimizing this norm. So the globally optimal solution can be derived using Euclidean projection. This is beautiful, but it is not biologically inspired. That's why I don't enjoy it. But it's an important paper. If this condition is not satisfied, then both sub-problems are solved again by using the latest available values. However, if the condition is satisfied, multipliers are updated, where the step sizes are calculated. Then they talk about sparse training, drop and grow schedule. Then they talk about sparse training, forward propagation and backward propagation, where the forward is this one. Z and B represent the output and biases before activation. And this is the convolution operation. But we define beta as a subset of weights from WL. This is the trick of this paper. This is one of the most important innovation of this paper. And set the rest of them with 0. So let's see. So if I is inside A sub L, because the else layer we have A sub L, then it's W. Otherwise it's 0. And A sub L is indices of active parameters in a sparse subset. The initial selection of those entries could be a random process or restricted to the top k proportion of the weights by magnitude. So this is what happens, the iterative drop and grow based sparse training process. So first we do random sparse and initialization, and you get our initial weight. Then second step, you go train delta t minus 1 steps. At the third step, we drop weights. You see they have dropped these weights. We drop weights with at least 2 absolute magnitude, and then we grow weights with highest 2 absolute gradient.